Okay. Grab your calculators. One of the ways that we can pick up the slack of finding the area under the curve, finding our value of our integral, is by using our calculator. There is a function on your calculator that will evaluate an integral, which is awesome if we are working on a problem where we are allowed a calculator, right? And that is called your fint function int, and on your calculator, and it is math 9. So if you'll hit your math button, option 9 is that fint. And then we have to fill it in. Now, it's a little bit different per calculator. The newer ones, which I'd say are most of them around the room, it's going to look something like this, and you just kind of arrow between the different dotted boxes up there and fill in your information very similarly to how it looks visually on a normal integral. You put your lower bound, upper bound, your function, and then it will always be the variable of integration, which is dx on our calculator, because we aren't going to put any other variable in there. If you have an older operating system, like a TI-83, I can't remember if anyone in here has an older one, this is more what it looks like. So we're going to have a little get to know your calculator moment. Let's use this example right here, which was the one from our warm-up that we couldn't do graphically. Go ahead and type it into your calculator and let your calculator evaluate that integral for us. And we should be getting, looks like 53.333. We're going to take a second and make sure everyone can get that on their calculators. Help each other out if you're not finding or getting that done correctly. Any questions? Okay, so now that's a second method for how to find or how to evaluate an integral. Graphically, geometrically, if it's a shape we can do. If we have a calculator, we can use that math 9. And we'll learn by the end of today a third option of how to evaluate an integral. Some integral rules that we have. First of all, the order of our integration, whether we go on that interval from a to b or from b to a, it will impact our value. So if we are looking at this and we go from a to b of some function, if I were to switch the interval from b to a, it will switch the sign on my answer. So for example, a very basic example here, if I were integrating from, let's say, 1 to 3 of the constant function 4, if you remember evaluating a constant function, it is difference in your bounds times that constant, right? So this would be a value of 8. Well, if I were to integrate instead from 3 to 1 of 4 dx, it would switch the sign on my answer. So now my answer would be -8. Correct. Yep. The direction that we move also will impact that. So it would switch our sign so that it'd be positive. So if the bounds of our integration are the same, we go from a to a of this function, we get an answer of 0. Why is that? We'll kind of give ourselves, again, another picture here. We've got some constant function up here, let's say, and I'm evaluating it from a to a. Well, as I connect that up here, if I were to think about it as like a rectangle, well, the base of that rectangle is 0. 0 times the height is an area of 0. That line has an area of 0, right? So if we integrate from a number to itself, it's an answer of 0. A constant multiple. If your function that is being integrated has a constant multiple, we can slide that multiple out, kind of like we could weight and multiply our derivative by a constant. We can weight and multiply our integral by the constant. So if we have a constant k here in front of our function, we could slide that k out front. Or with actual numbers to look at, let's say we're integrating 5x dx. That would be the exact same answer if I were to slide that 5 out and integrate from 1 to 3 of x dx. And as we get to the end today, you will see that that might make some of those type of problems where we'll do those by hand a little bit easier algebraically to do, is that you can always slide those constant out front. And then my reminder to you on the bottom of that page, negatives are a constant. It is just being multiplied by -1. So if my function is being multiplied by a -1, I could slide that out front, integrate the constant f of x, and then multiply our answer by a -1. Okay, next rule, the sum and difference of functions and integrals. If inside of my integral I have f of x plus g of x or f of x minus g of x, I can split right there at that plus or minus and do the integral of each of those functions individually. The integral from a to b of f of x, whatever sign had been between them, plus or minus, the integral of a to b of g of x. And again, as we are trying to break down finding the antiderivative at the end of today, sometimes thinking of it as individual integrals can make it an easier process. Additivity of your integrals says this: if I've got an integral from a to b of this function, and then the next one I'm adding goes from b to c, if where I stopped this integral is where the next one picks up, we don't have to break the integrals. I could then say, okay, well, if it goes from a to b and then from b to c, I can just keep it going, if those two are the same, and say that I'm going from a to c. Anyone still need this page? Okay. So this is a common way of kind of showing that we know these rules and can apply them. The thing that you see at the top, use the rules of definite integrals, and then they give us some suppose this information is true. We're going to use that for like the next 6 problems, so you don't have to write it down this page and the next. It's going to be the same thing, and that is this. The integral from -1 to 1 of f of x dx equals 5. The integral from 1 to 4 of f of x dx equals -2. The integral from -1 to 1 of h of x dx equals 7. And then we're going to answer some questions related to those given pieces of information. Below it says, find each of the following integrals, and then it does clarify, if possible. We are a little bound by just those 3 pieces of information at the top. We don't really know what the function f of x is or h of x, and so if it's not given to us, we can't really answer questions, so we may get to a point where we say something's not possible because we just don't have enough information. Okay. So on the first one, question is, what is the value of the integral from 4 to 1 of f of x dx? What rule are we seeing there? Yeah, where it switched my order of integration. Instead of going from 1 to 4, it went from 4 to 1. So if our answer when it went from 1 to 4 is -2, what's our answer when it goes from 4 to 1? 2, the opposite sign, right? Okay. Next one, if it goes from -1 to 4 of f of x dx, that is our additivity, right? We start here at -1, go up to 1, which connects to this one, which means we don't have to break. We can put the 2 together. It is the combination of those 2. So we would be able to add the 5 and the -2 to get the total of 3. Questions on that? Okay, I'll give you a second to look at this next one. The integral from -1 to 1 of 2 f of x plus 3 h of x dx. A couple different things going on in this one. One of the things we see in this one is that we have the sum of two different functions. And so I can break it at that sum and do the integral of the first plus the integral of the second. And then the second rule we're seeing happen in that one, your constant multiplier, right? I don't actually know what the integral from -1 to 1 is of 2 f of x, but I do know what it is of just plain f of x. But that constant can slide out front. Okay. Same thing over here. Slide that constant out front. Oops, h of x. And now those are all values that I know. The 2 is still there, and now I know that the integral from -1 to 1 of f of x dx is 5. And same thing here, the 3 slides down, and the integral from -1 to 1 of h of x is 7, for a total of 31. Questions? Okay, so sticking with those exact same 3 pieces of information at the top. First question on this page, what is the integral from 0 to 1 of f of x dx? Okay, do we have at the top the integral from 0 to 1 of f of x dx? No. This is what is very tempting on this one. I have one that is similar to this, and it goes from -1 to 1. Well, if we only go from 0 to 1, wouldn't that just be half of this? And so would our answer just be 5/2 or 2.5? No, do we know how that area is spaced under that curve? So we don't know that it splits equally on either side of 0, do we? So we can't do that. We just don't have enough information. This would be not possible. Okay. Kind of on that same idea, we have, now the next one it says of h of x dx. Well, the only thing we know about h of x dx is that the integral from -1 to 1 is 7. And they're asking us from -2 to 2. So again, going from -1 to 1 and expanding that by doubling it, would that expand my area by doubling it? Again, we don't know what function we're looking at. We don't know where or how that area is spaced in there. So again, we just don't have enough information. This one is not possible. Now, if you notice, everything on this page has been not possible, right? So as we look at this last one, I'm going to go ahead and tell you it's not possible. And I want you guys to figure out why. Okay, if I'm telling you it's not possible, what part of this next one is making this one a not possible question? Yeah, we're fine through the f of x part of it, right? I can figure out from -1 to 4 of f of x, and I can figure out from -1 to 1 of h of x, but we don't have all the way to 4. So because this was part of it, and we are stopping the information we know at 1 for h of x, this one would also be not possible. Any questions on this? All right. This next topic is, the process is easy. Fully understanding what's going on is not always as easy, because I think the visual might actually mess with you a little bit here. But it says this: if f is integratable on the interval from a to b, then its average value, or its mean value, on that interval from a to b is given by this formula. The average of f is 1 over b minus a, and b and a are the ends of our interval, times the integral from a to b of f of x dx. Okay, so let me see if I can do a visual here that may or may not help us understand what's going on here. Is that we're given some integratable function. Let's say f of x looks something like this, okay? Some integratable function, and we are looking at it on the interval from a to b. Okay? And it talks about its average value. Now remember, the values are its y values on this function. And they're asking, okay, so on this interval from a to b, what is the average value of this function? Okay. Well, our formula talks about the area under the curve here. Okay, which again, not necessarily a shape we know, but what the mean value theorem is saying is that we've got somewhere, some value here, such that if I were to use this as the height of a rectangle in that same interval from a to b, that the area under that blue rectangle would match the area of the green that I have highlighted. And that's the average value of the red line on that interval. So if I can get the area of that rectangle to match the area of the under the curve, the height of that rectangle is the average value of that function. That's what it is doing in this formula. The formula itself is pretty easy to just chug and plug there. 1 over b minus a times the integral from a to b of our function. But that's what it's doing. Okay, it's finding that average value of the function. So let's look at an example of a problem that uses that. It says using the fint or math9 command on your calculator, find the average value of f of x equals 4 minus x squared on the interval from 0 to 3. And then the second question says, does f actually take on that value at some point on that interval? Okay, so let's start with the first question. Find the average value of the function on the interval from 0 to 3. So our average value is going to be 1 over b minus a, which in this case would be 3 minus 0, times the integral from 0 to 3 of our function, which is 4 minus x squared, dx. Then we go to our calculator. Now, I would just do the fraction by itself for a second here. 1 over 3 minus 0 is just 1/3. And this I'm going to do using math9. Okay, so again, kind of practicing getting that typed in our calculator. And what is the value of that integral from 0 to 3? Okay, so then the average value of this function from 0 to 3 is 1. So then the second question, does it actually take on that value? Does our function actually take on that value at some point on the interval? Well, the question's asking, does it equal 1 somewhere on the interval from 0 to 3? Well, we just set it equal to it. Does it ever equal 1? And if so, is it on the interval from 0 to 3? So I set it equal to 0, or set it equal to the average value that we just got, right? Solve for x. Looks like we do get an answer here, right? It will equal 1 if x equals square root of 3. It will equal 1 if x equals negative square root of 3. But there's one last little twist to this. Do either of those two x values fall on the interval from 0 to 3? One of them does, right? So yes, it does. It will equal 1 at that point where x equals the square root of 3. So yes, in our justification, the square root of 3 exists on the interval from 0 to 3. Questions on that? All right, the last piece that we are going to get into today actually is going to be one of our bigger topics, or one of our more important things, and this is actually kind of your third way of evaluating an integral. The first way we had to evaluate an integral was graphically, using our geometry, draw a shape, find its area. The second way we just learned at the beginning of class, and that was grab my calculator and hit Math 9. The third way is using what's called the antiderivative. Okay? And so as we look at this one, it says that our integral from a to x of f of t dt will equal, and then it's got this capital F of x, the top end of our interval, minus capital F of a. Well, capital F actually means something. That's not just a typo or anything. It is representing what's called your antiderivative. Or in other words, f, which was what was inside our integral, is the derivative of this function. Now, we did that a little bit first semester, where sometimes I'd be like, hey, this equation is f prime. What would have been the function it came from? Well, what you guys were doing was finding an antiderivative. Okay? But now we're going to use that a lot, thinking backwards through derivatives, to be able to help us do something like evaluate an integral. Okay, so how do I do that? It's called evaluating our integral analytically. Okay, well, the first thing I'm going to do is look at this and say this right here is f of x. The first thing I'm going to do when evaluating this analytically is figure out what capital F, our antiderivative, is. So capital F of x is, and as I look at that number, I kind of have to do a little bit of slow down and think, how would I have gotten to something like that? And we're working our way backwards, not taking a derivative, but untaking a derivative, right? And this would have been done by power rule. Is that all looking okay? So if I recognize, okay, yes, that would have been done by power rule. And I know this is a pretty basic one, but just to kind of help you with some future problems here. So that means that whatever exponent this started at, I would have subtracted 1 from this number to get to this using our power rule, right? So undo that. To move from here to here, we would add 1 to the exponent. Okay? Now, the other part of it is always this. In the power rule, yeah, we subtracted 1 here, but didn't we first take that times this number? So there's a couple ways you can think about this. Yes, I take that times this number to get this. So 2 times something gives me 2. What's the something? The other way you can think of it is to move from this number to the number down here, you are going to divide by the new exponent. So if I took 2 divided by 2, that's this number right here. Okay, if you need some help of thinking of a way, if you're having a hard time thinking backwards through that, that's another way that you could kind of do that, is take this number divided by your exponent. That's what would have been here. Yes? No. To match your book. No. Other questions? Okay, so once we have that, 2 divided by 2 is 1. Our antiderivative, f of x, is x squared. To then use this antiderivative to evaluate our integral, we will do f, capital F, of the upper bound, 5, minus capital F of the lower bound, which I kind of wrote over there, but is 2. And all we're doing is plugging those into our function and taking the difference between our two answers. So f of 5, capital F of 5, that goes in right here, 5 squared, minus 2 squared, or 25 minus 4. And our integral would evaluate to 21. Any questions on that? Okay, so let's try a couple here. Using that, so find the following analytically by using antiderivatives. Just giving you a little preview of where we're headed with this. When you are doing this, a lot of times you'll be asked to justify using calculus. To do that, you need to clearly label and show your antiderivative. So what is capital F of x? And then clearly show what equation you would use to get to your answer. What are you plugging in, and in what order, and what operation are you doing between those? knowing that we are in AP calculus, doing something that like, oh yeah, I did all that in my head and the answer's 5, we get like none of the points, right? Showing our work, supporting with calculus. I'm going to start by clearly showing my antiderivative. If our derivative was secant squared, our original function was tangent. Our antiderivative is tangent of x. So then I would do f of pi over 4 minus f of 0, or tangent of pi over 4 minus tangent of 0. And this is where I have to remember my unit circle if I don't get a calculator. What is tangent of pi over 4? Tangent of 0? 0. Questions? If I was supporting my answer with calculus, the only thing that I would feel comfortable maybe not showing would be either of those lines, but definitely showing all of that. Okay, so make sure that we are not skimping too much on our work. All right, let's try one more here. Integral from -1 to 2 of 3x squared dx. Okay, power rule again, right? 3x squared. Let's find its antiderivative. If it started out as an x squared, its antiderivative would be an x cubed. And the number in front of that? 1, because 3 times 1 gives me 3, right? Or take this number divided by our new exponent gives me the number in front. So then we should have done our antiderivative of 2 minus our antiderivative of -1. 2 cubed is 8. -1 cubed is -1 minus -1 is plus. We get an answer of 9. Okay, we're not going to do a full integration of something right now, but I want to give you a little bonus to think about here. If I told you that our function inside the integral was 1 over x, talk to your table partner about what its antiderivative was. And if I told you that the function inside our integral was 1 over x squared, talk to your table partner about what its antiderivative is. Go. There's a very, very good reason that I picked these two. Did anyone get that first one figured out? What did you guys pick? Natural log. Remember that one? We haven't talked that in a while, have we? Natural log, right? Natural log, derivative of natural log of x is 1 over x, right? There it is. Okay, these two mess with me because I feel like they should have similar antiderivatives, right? And they don't, because 1 over x is natural log of x. It might help you if I wrote the second one like that. Does that help anyone? Instead of looking at it as 1 over x squared, if I write it as 1 over, x to the -2. Think about how we did our power rule earlier. If this is the exponent we ended at when I did my derivative, that means I took this and subtracted 1. So work your way backwards. Take that and add 1, right? So we're looking at -1. this number times this gives me the number in front of x. Or take this number, divide by this, gives me the number in front of x. This number is -1. Okay, well, we don't usually see it like that. -1, x to the -1 is -1 over x. Questions? We can do this. We'll get there. Got to dust off the derivative rules, right? All right. Your assignment out of the book, page 294, a bunch of random ones.